So our denominator here does factor. So I would be thinking about breaking this apart with partial fractions. And I'm going to pause for a second about what we would put in the numerator for this function. When we have a rational function, we always want to check our power in the numerator versus our power in the denominator before we keep going on. So our power in the numerator is x to the first, and in the denominator, it's x cubed. So our power is lower in the bottom, which means, and here's kind of how I remember it, my power is lower in the bottom in our original function over here. That means that when I'm breaking this apart with partial fractions, the powers in my denominators should be less than the power that I put in the numerator. Because this is a linear term, x plus 3, or my power in x is 1, then what I'm going to put in the top is essentially an x to the 0 power, or a constant. Because that x minus 2 plus 1 doesn't factor anymore, it's called an irreducible quadratic. This has a power of x squared, which means what goes on top needs to have a power that's less than x squared. And the most generic term that I can put on top with a power that's less than x squared would be a linear term. So really the thing to remember is that when you have an irreducible quadratic, meaning something of an x squared, but it doesn't factor anymore, then the term that you want to put on top when you're doing partial fractions should be a linear term. Bx plus c, ax plus b, pick your letters, but it should be a linear term on top. Just for fun, let's go ahead and actually finish this off. Thinking about solving this out with partial fractions, first step, I'm multiplying both sides by that common denominator. Distributing that through, on the left-hand side, I get 2x plus 1, and on the right-hand side, when I distribute this out, my a will be multiplied by x squared plus 1, and then bx plus c will get multiplied by x plus 3. Thinking about our two different methods for solving for the constants a, b, and c, this is actually a case where I think it's good to know both ways, because I would actually kind of do a hybrid of the two. If there are nice numbers to plug in that are going to make something go to 0, I start with that. So looking at this, if x is equal to -3, this term is going to go to 0. So I'm going to start there. So if x is equal to -3, then on the left-hand side, I'm looking at -6 plus 1, or -5. This whole term is going to go to 0 once I plug in -3 for x. And here I'm going to have, well, -3 squared is 9 plus 1, so that's 10. So a times 10. And it looks like a would equal -1/2. I've essentially run out of nice numbers to plug in at this point. Since I've run out of nice numbers to plug in, I'm actually going to switch gears to the other method where I'm going to distribute everything out and match up coefficients. This side's already done for me, 2x plus 1. Here, when I distribute out the coefficients, I'll have ax squared plus a. This is going to be a little bit messy, but bx times x, I'll have bx squared. Bx times 3, I'll have 3bx. c times x, and 3 times c. Then I'm going to come back in here and remember, we already know the value of a, which means I can replace that a and that a both with -1/2. Now it's time to match up coefficients. On the right-hand side, I have 2 terms with an x squared. But on the left-hand side, essentially I have no terms with an x squared, or if you want to think about it, I can write in a placeholder of 0x squared. That means that 0 should be equal to -1/2 plus b. Looking at my terms with x, on the left-hand side I've got 2x, and on the right-hand side I've got 3bx plus cx, which means 2 will have to be equal to 3b plus c. And finally, matching up our terms that have no x values at all, 1 would have to equal -1/2 plus 3c. Well, it looks like I don't even need this equation, because that's going to give me b, and that's going to give me c. If we hadn't gone ahead and plugged in the value to get a first, this would have been messier to deal with, because it would have still had an a in it, and this would have been messier to deal with because it would have still had an a in it. So that's why I said kind of having this hybrid of, if there are nice numbers to plug in, do that first to get any of the constant values, so that the equations that you get when you match up coefficients are easier to work with. So our b is 1/2, and here 1 plus 1/2 would make that 3/2 is equal to 3c, or c is equal to 1/2. Other questions from that, or did we want to actually finish off the integral now that we've done the partial fractions part? Or should we call it a day? Yes, there was a request to integrate it. Yes, I'm happy to integrate it. Okay. Gonna erase all of this because I need the space. First one, straightforward. It's just another natural log. I'm looking at -1/2 ln x plus 3. For this second one, just because I don't want to look at the fractions, I'm going to go ahead and factor that 1/2 out. So that's 1/2 the integral of x plus 1 over x squared plus 1 dx. I would look at that. We already know it's not a partial fractions problem. X squared plus 1 doesn't factor. I do want to check really quickly to see if I've got a u substitution, and sometimes we're lucky. But the derivative of the bottom would be 2x. It wouldn't be something plus a 1. So here's the trick that is going to happen most of the time when we have an irreducible quadratic like this in the denominator. We're actually going to want to, even though we solved this as if it said ax plus c on top, in order to finish the integral, we want to break this apart into two pieces. Once we break it apart into two pieces, this one we will have a u substitution for, because the derivative of the bottom is almost what we have on top. If u is x squared plus 1, du is 2x dx, or 1/2 du is equal to x dx. Bringing this one along for the ride, got negative 1/2 natural log of x plus 3. Rewriting this, I have this 1/2 and another 1/2 that's coming from my du. So I'd have 1/4 the integral of 1 over u du. And this last one, hopefully we're starting to recognize whenever I have 1 over x squared plus 1, that's arctangent, or tan inverse. So that's going to be 1/2 tan inverse of x. I'll go ahead and add in our plus c. So I'm looking at negative 1/2 natural log of x plus 3 plus 1/4. That integral would be natural log of u. And I'm going to go ahead and just plug the u back in. So ln of x squared plus 1 plus 1/2 tan inverse of x plus c. And that whole thing would be my final answer.